and thanks to all of you for coming over here to attend this program. So I will be talking about giant black holes in the cosmos. So this lecture will introduce you to an enigmatic entity of the universe, that is a black hole. We will also learn that how and why all the galaxies in the universe harbors a huge black hole at its center, and what are the roles of the black holes in the evolution of the galaxy as well as the evolution of our entire universe. Also, we learn that the environment of the black hole, that means the space-time surrounding the black hole, how that helps us to understand the Einstein's theory of relativity, both special theory of relativity as well as the general theory of relativity. So to begin with, let me address a very simple yet profoundly important question, that what everything on Earth is made of. Yeah, so what everything on Earth is made of. So from your class 2 course, the high school course, you know that any chunk of matter can be disintegrated into molecules. Molecules can further be disintegrated into atoms, and atoms can further be decomposed into electron, proton, and neutrons, and those subatomic particles are further composed of further more fundamental and smaller particles like quarks. Now, this procedure that that the attempt to understand the structure of a complex system by decomposing it into smaller constituent particles of the system and trying to understand the properties of the smaller system, and then to gather such knowledge to understand the properties of the larger system. The whole procedure is called reductionism in philosophy. So that means that you reduce the structure of a complex system into smaller constituent system and try to understand the properties of the smaller constituent system, and from that particular knowledge you try to understand the overall bulk property of the entire complex system. For example, for BSc students, you know the thermodynamic properties of the gas, let us say pressure. So when we need to understand the pressure of a gas, we can also kind of decompose the gas into its constituent molecule, try to understand how the kinetic theory of gas creates the concept of pressure, try to write down Maxwell equations or Maxwell-Boltzmann distributions, etc. And then finally go from there to partition function or whatever to understand the pressure. So that's precisely what reductionism is in philosophy or in general branch of knowledge. So if we would like to take one step ahead and to understand that how the reductionism works, to understand the large-scale structure of the visible universe, that our entire universe. What our entire visible large-scale universe is made of? The answer is a galaxy of different shape, size, mass, and morphology that constitutes the universe. So different galaxies of different natures are actually the fundamental building blocks of the large-scale structure of the universe. So just for your reference, that these photograph of distant galaxies have been taken using the famous Hubble Space Telescope. This Hubble Space Telescope, as you know, was served as probably the most important and most versatile telescope in the history of the human civilization. But you know, recently that has been replaced by a more powerful telescope called James Webb Space Telescope, which started operating very recently. The last year in 25th of December, and this year in 12th of July, they published the first set of data and things like that. So now, if we would like to pick up one galaxy from this entire set of galaxy, let us, for example, our own home, our own Milky Way galaxy, then it somewhat looks like this. So this is an artistic equation, it's not a photograph. That the galaxy has a central core, the bulge of a lot of stars, and it has several spiral arms, and the stars are also there in the spiral arms. And we are sitting over here, that is our solar system, that is located something around 26,500 light years away from the center of the galaxy. And you know the light year is a certain distance, that is the distance covered by the light in 1 year, and which is equal to 10 to the power 13 kilometers. So our solar system is around 26,500 light years away from the center of the galaxy, and the center of this entire galaxy is rotating above its center with a very high velocity. It's something like 230 kilometers per second, so which is a pretty high number, pretty large number. And along with that, the entire galaxy is moving through the space. That is also with a very large velocity, like 550 to 600 kilometers per second. So, the time taken by the solar system to revolve entire circle around the center of the galaxy is sometimes called cosmic year. So, till the birth of the sun has, the solar system has covered 21 whole circles. The life in Earth was originated some 17 cosmic years away or something like this, and one cosmic year is something around 225 or 250 million years. So last time when we were here, so that was the Jurassic Age, so the dinosaurs were roaming around probably here as well. So this galaxy has some typical numbers associated with it. For example, the overall extent of the galaxy is 1.5 to 2 lakh light years, and it contains something around 400 billion of stars, and stars have their planets, and some of the stars have their own planets, or all the stars have their planets. So there are roughly around 100 billion planets, and out of those 100 billion planets, roughly around 11 to 12 billion planets are supposed to have the signature of the light, at least theoretical. And the mass of the galaxy is huge. It's something like 1.5 trillion solar mass. That is 1.5 to 10 to the 12 number of suns. The total mass of the 1.5 to 10 to the 12 suns is equal to the mass of the galaxy. That's a huge number. So I just want to give you an idea that how the large numbers are associated with astrophysics and how we deal with very large numbers. That will be useful in the later part of the lecture. But the interesting thing is that this kind of very large number, for example, 1.5 into 10 to the power 12, so that means 1.5 trillion, that number has its own analog in our terrestrial life as well, in smaller system. This is something like looking the universe in a droplet kind of thing. For example, you'll be surprised to know that on the entire surface of our body, the number of bacteria resides is something like 10 to the power 12. So the mass of the galaxy is 1.5 into 10 to the power 12 solar mass. Number-wise, that is equal to the number of bacteria which resides on the surface of our body. So this is the science is very interesting. That's what I want to say. So now this is the artist's impressions for our galaxy, and in real life, it looks like this. That it runs like a patch of the this lighted band in the dark sky, as if some milk has been poured on the surface of the sky. So that is why the galaxy is called our Milky Way galaxy. Actually, there is an association with the name galaxy and the milk. I'll come to that point later on. But there is a very interesting Greco-Roman mythology of the origin of the galaxy, how our Milky Way galaxy was formed. The story is something like that she is Hera, the queen of the deities in Greek mythology, and this is Zeus or Jupiter, the king of the gods. And Jupiter has his son Hercules, and he was not the son of Hera, he was son of some other lady called Alcmene. Alcmene was Andromeda's granddaughter, and since Hercules was born to a mortal woman, Alcmene was not God, so Hercules was not immortal. So Zeus wanted Hercules to be immortal, so he put Hercules on Hera's breast so that Hercules can start breast milk from the Hera. Hera that time was sleeping, and when she woke up, she found that some mortal entity is sucking her milk, so she threw away Hercules. So milk from her breast spurted towards the sky, and some of the spurt fell on the ground. So the milk from her breast, which was spurted towards the sky, that created the galaxy Milky Way, and the milk which fell on the ground, so that created the lily towers. That's a very famous Greco-Roman mythology, and this oil painting, the huge oil painting, 5 by 5.5 feet, has been kept in the Royal Gallery of London. Was painted by late Renaissance period Italian artist in Toledo. And you know, another interesting thing is that the name of the galaxy or the Milky Way was first introduced by British poet Geoffrey Chaucer sometime in 1380. Chaucer was very famous British poet. He is sometimes called as the father of modern English poetry. And one of his most important, or rather most famous contribution in the English literature is called the Canterbury Tales. And in one of his book of poetry, which is called the House of Fame, he first used the word galaxy. So it's written in the Old English, the sea, the galaxy, which means the Milky Way, for it is we. So it was an Old English kind of thing. So it's technically called Middle English. It was influenced by the Italian language kind of thing. Like for example, the kind of language what other Italian famous poets used to use, like Giovanni Boccaccio or the Virgil or the other Dante Alighieri, for example. So it means that sea and the sky to the galaxy. Galaxy was the word used by Chaucer first, which men claim the Milky Way, which men call the Milky Way, for it is white, because it is white. So that is, look at the sky, something white you will see. Since it's white, so it's called galaxy. Why the white thing would be called galaxy? Because the Latin of the milk is called lactea. Lactea, from where you know the lactose is the protein associated with the milk, and the Greek term for the milk is called gala. So gamma, alpha, lambda, alpha. So this is gala. So that is why the galaxy and the milk are kind of associated from the white color. Also, one of the extremely important contribution of the Chaucer was the book which is called the Treatise of the Astrolabe. So there is an instrument in astronomy in older days which was called the astrolabe. The astrolabe was used to kind of find out the inclination of the celestial object from the horizon. So technically it is called the inclinometer. So Chaucer wrote a user's manual in English for the astrolabe, and that was probably the first ever instruction manual for any instrument written in English language. So why I am showing this thing? Because this is very interesting. So initially, or even now, so there is not that distinction between the arts or humanities or science kind of thing. It's a question of pure interest. It's a question of pure interest as philosophical level. So you know that an artist is drawing something about the origin of the Milky Way. A famous poet is writing user's manual for an instrument and things like that. So okay. So now suppose I would like to ask the next question, that what is the energy budget of our universe, or what is the energy budget of the galaxy? That is, what exactly is happening inside the galaxy which actually fuels the galaxy. That means how we can observe the galaxy. Now we know that the galaxy is a combination of large number of stars. I told already that our Milky Way galaxy is composed of around 400 billion stars. So then to answer the question of the origin of the luminosity of the galaxy is actually requires the knowledge to understand how the stars shine. That what exact physical process is happening inside the star, so that a star actually shines. So this is a famous painting of Dutch painter Van Gogh. The name of the painting was Starry Night, which was painted in a stormy night in the Arles, in a place called Arles in France. So the fundamental question, one of the most fundamental questions in the astronomy is what makes a star shine. So that means what physical processes is going on inside the star so that we can observe the star and the stars are luminous. So you people also know the answer of the question, that is actually nuclear fusion, which actually powers or fuels the star. What is a nuclear fusion? Nuclear fusion is a thermonuclear phenomena where two small atoms fuses into a larger atoms, and there is something called mass defect, that the total mass of the small atoms is slightly less compared to the mass of the large atoms, and the mass deficit, that means the difference of the mass is actually gets manifested through energy, and that energy actually fuels the star. So that's actually energy generated through the thermonuclear fusion. And what is the amount of the liberated energy? The amount of the liberated energy can be calculated through Einstein's famous equation E is equal to mc square. That if you can completely disintegrate an amount of mass, then the total amount of energy available from that process is that amount of disintegrated mass into square of the velocity of light in vacuum. However, there is a catch, that there should be some efficiency factor in front of the mc square. Why? Because let us try to understand, because this is going to be the extremely important topic of our future discussion. That suppose in this equation E is equal to mc square, I assume that m is the amount of mass totally disintegrated. Now, if I ask the question in a slightly different way, that suppose you consider m amount of mass and try to see that after the disintegration of certain amount of mass out of m, what will be the amount of energy liberated. So that means the total amount of the mass taking place in the reaction will not get disintegrated. It will only a part of the mass which will get disintegrated, and which part of the mass will get disintegrated depends on the efficiency factor of the thermonuclear process, and that efficiency factor is actually eta. And so by studying all different thermonuclear processes, we find that the most energetic thermonuclear processes, like for example the fusion of deuterium and tritium, which gives helium nucleus and some energetic particle, that gives you the largest possible values of the eta, which is something like less than 1%. So that means in most energetic nuclear fusion procedure, we can convert only less than 1% of participating mass into energy. So that's extremely important information in connection to the rest of our talk. So so far so good. So we wanted to understand how the stars shine, and we wanted to understand how the galaxies are visible, what is the reason for the luminosities of the visible galaxy, and we understand how the stars shine through this thermonuclear procedure. So we kind of get satisfied. That's all right. So we now understand the energy budget of the galaxy as well as the energy budget of the entire universe. That we can now understand how the galaxies shine. Fine. So that was the picture in early 60s. In 1963, something very interesting happened. This professor of astronomy, famous Professor Martin Smith from Caltech, California Institute of Technology, was observing some astrophysical object called 3C273. This name is a technical name. So this 3C means Third Cambridge Catalog. So in Cambridge University, they prepared a catalog for astronomical objects, and there are different revisions of the editions. First edition, second edition, third edition. So 3C corresponds to the Third Cambridge Catalog, which was prepared sometime in 1959. So this object was the 273rd entry in the Third Cambridge Catalog. So what Martin Smith wanted to observe this thing for the radioluminosity of this object, that is, he wanted to understand how much radio wave is being emitted from that particular object. He found something very unusual kind of thing that he found that the energy emitting region of the 3C273 is pretty small. Is pretty small compared to the size of an entire galaxy, but little bit larger than a star, as if it's almost a star. So technically it was called a quasi-star. So that was small amount of matter was ejecting huge amount of energy, which kind of does not match with this theory. So that means if you have a eta which is less than 1%, then there should be an upper limit of certain amount of mass which will be, what will be the amount of liberated energy, right? For example, if you take 10 gram of mass and that 10 gram of mass just takes part in a thermonuclear process, and then what will be the maximum amount of liberated energy, then you should have an estimate because you know that the largest value corresponding to eta is less than 1%. So here, from the observation, the mass has been detected for this 3C273, and corresponding to that mass, the amount of energy is ejecting was enormously large, and that was the source of the major confusion that thermonuclear process cannot explain the energy generation mechanism from this kind of object. And because that was very surprising or rather weird at that time, because people over the entire world, the entire scientific community were convinced that the most energetic process in the universe is actually associated with thermonuclear fusion, but this is far more larger compared to the amount of thermonuclear energy. So what exactly it is? So this is just for the completeness. I show the front page of the paper, which was published in Nature in 1963. The title is 3C273, a star-like object with large redshift. So not only it was ejecting a huge amount of energy, it was also a very bright radio emitter. That means it was actually emitting lots of radio waves. So it was named as quasars or quasi-stellar radio objects. Okay, and eventually a large number of such quasars are found, and eventually it was found that quasars are actually a subclass of certain particular quantum entities which are called active galactic nuclei. So active galactic nuclei are the nucleus of certain kind of galaxies which are very active. That means at the center of some galaxies there are a lot of activities going on, because of which huge amount of energy is coming out. How huge it is something like, for example, 10 to the power 46 hours per second. That's a very large amount of energy, because that energy is equivalent to the disintegration of several solar masses per year. So that means if you completely disintegrate several suns in 1 year, then the amount of energy we get through E is equal to mc square will be something like this. But it was observed that no such process is happening, that not several solar masses per year are getting destroyed. So what is the source of the energy? That became the prime question. And so George Gamow, famous scientist, you must be knowing his name, the Russian nuclear scientist. So he wrote a modified version of the this nursery rhyme, which was published in the famous American magazine Newsweek, 1964. The twinkle twinkle quasi-stars, biggest puzzle from afar. How one like the other ones, brighter than a trillion suns, twinkle twinkle quasi-stars, how I wonder what you are. So before I get into the solution, what was actually fueling those active galaxies, let us just have a look at the pictures taken by Hubble Space Telescope of certain number of galaxies. So this is called this Arsingas galaxy, and this is called this active galaxy Centaurus A, and I focus the central part of the central galaxy so that you can understand that they are extremely bright, and if you further if you further zoom in the central part, and then you find that there are the presence of the cyanogen gas, which has blue colors, and the presence of the sun in gas in the astronomy indicates that there are a lot of stars which are forming. So the active galaxies are not only producing huge amount of energy, also it's a prominent star formation zone. So what exactly is happening at the center of the active galaxy for which a huge amount of energy is coming out? So people try to answer this question through the black hole hypothesis. There are a lot of works in the field, but credits are mostly given to these four scientists. So Yakov Borisovich Jelovich, a Russian scientist, Erwin Sol. So he is no more. So he died a number of years back. Erwin Solpeter was a professor in the Cornell University. Professor Donald Lindenville from the Cambridge University. Professor Igor Dimitrievich Novikov from Denmark. So their proposal was that at the center of some galaxy there are accreting supermassive black holes which are actually fueling the galaxy. So now what is accreting supermassive black hole? That in last 10 minutes I will try to explain. So what is a black hole? Black hole in general is the end product of a star. So how are the stars formed? The stars are formed from the molecular cloud. So this is a photograph. Once again, I was just a photograph of the molecular cloud. This dark patch. Molecular cloud is relatively colder cloud or clump of the gas floating in the sky. So this may be very large in size. This particular molecular cloud is called Barnard 68. So this cloud was named by astronomer Professor Edward Barnard. So just to give you a feel of the number, so this molecular cloud, the mass of the molecular cloud is 2 solar mass, and the temperature of the molecular cloud is very low, from 16 degree Kelvin, and the extension is 0.2 light year, and this is something like 5 light months away from us. So this is so cold that light cannot pass through this thing. So the stars behind the molecular cloud are not observable. So it looks bad. So what actually happens in the cold molecular cloud? There is a gravitational pull inward to condense the molecular cloud, to fragment the molecular cloud, and the star starts forming. And once the stars form, it survives under something called hydrostatic equilibrium, that you have thermal pressure outside. That thermal pressure comes from the thermonuclear reaction happening at the center of the star, and the gravitational pull inward. And by balancing the gravitational pull and the thermal pressure generated due to thermonuclear reaction, a star retains its spherical shape. Now, after a long time, the entire fuel gets completely consumed, and then what happens? A small star starts evolving. First, it becomes something called red giant. It pops up. Then there is a small explosion and becomes planetary nebula, and then something called white dwarf, extremely dense object in the universe that forms. If stars are pretty large, then the large stars become red supergiant. And then there is a huge explosion called 50 square V equals U plus etc. So in current space-time, there are equations corresponding to geodesic, that how a particle will move, and there are equations corresponding to the force, that how the matter, background space-time, curvature, etc. will interact with each other. I'm not getting into the detail. So this is our famous Einstein equation. And the solution of the Einstein equation is actually called black hole solutions. So Einstein first provided this equation in 1915, and almost immediately after Einstein, Professor Karl Schwarzschild from Germany, he provided a theoretical exact solution of the Einstein equation, which gives you the structure and the space-time of a black hole, which has only mass. And later on in 1963, Roy Patrick from the New Zealand, he published a paper in a famous journal called Physical Review Letters, where he solved this Einstein equation and provided the soul is something which is surrounded by the one-way membrane called event horizon. The matter can only pass through the event horizon along one way, it cannot come back. So the black hole cannot emit anything, and it creates a so strong gravitational field surrounding it, so that nothing can come out of the gravitational field, not even light. So that is why black holes are entirely black. You cannot observe it. Okay. However, there are different kinds of black hole. The kind of black hole what I was talking about in connection to Chandrasekhar's or actually stellar mass black hole, that the remnant or the end point of the life cycle of a star. But for our initial purpose, that what actually is fueling the active galaxies, that requires the concept of the supermassive black holes. The supermassive black holes are very large black holes which are sitting at the center of the galaxies with mass billion to billion solar masses, and they form in a completely different way. Okay, and now the question is, if you have an event horizon so that nothing can come out of the black hole and black hole remains entirely black, how it's possible to observe a black hole at all? It's possible to observe a black hole, at least theoretically, through some process is called accretion. What is accretion process? Accretion is the infall of the matter onto the black hole because of the black hole's gravitational attraction. Why it will produce energy? The logic is something like this. For example, you take a piece of chalk and release it. It will finally drop onto the floor and you will hear a sound that the chalk is hitting the floor. So why the sound? Because while falling onto the ground, it acquires a certain amount of gravitational potential energy, and when it stops, its velocity becomes zero. Then the amount of potential energy acquired will be converted into other form of energy, that is sound energy. So you will hear a sound. Now, if you kind of release the chalk from an infinite distance, or if you increase the gravitational field to an infinite strength, then the amount of the gravitational potential energy acquired will be extremely large, and the amount of energy released to the conversion of the gravitational energy will also be extremely large, and that will come as a emergent electromagnetic energy or emergent electromagnetic radiation spectrum. And we study the emergent spectrum and try to understand that is a black hole, because black holes has extremely strong gravitational field surrounding there. So if something falls onto the black hole, huge amount of gravitational potential energy will actually be converted into different form of energy like emergent electromagnetic energy, and that electromagnetic energy will provide you certain emergent spectrum. You try to observe the spectrum through certain satellites, for example, X-ray Newton, which operate in X-ray, and then you will be sure that, okay, so the black hole is sitting over here. So that is the indirect process of identification of the black, theoretical kind of thing. And there are something called accretion disk, that if the matter falls onto the black hole as angular momentum, then before falling onto the black hole, it gets settled in a disk-like structure, and that is called accretion disk. So this is actually the energy generation mechanism of the active galactic nuclei. So this is the basic essence behind that black hole paradigm. That at the center of the active galaxies there are huge black holes. Matter is falling onto the black hole, and the infalling matter releases a large amount of gravitational potential energy, and that large amount of released gravitational potential energy is coming out at electromagnetic radiation in the form of emergent spectra. You focus your satellite to the emergent spectra, you try to observe the emergent spectra and try to speculate that the emergent spectra is due to the infalling material onto the black hole, and the black hole is sitting at the center of the galaxy. So that is the overall idea, that why the galaxies will contain a huge black hole at the center. So not only a black hole will have matter falling in, but also a black hole will. So these are some of the photographs taken by Hubble Space Telescope of active galaxy. At the center is very much luminous and is surrounded by huge dust disk. That is not accretion disk. Accretion is much smaller, but that's a large dust disk which is the source of the matter which is actually falling onto the black hole. And then some of the galaxies show the signature of the jet, that some matter is coming out at both the direction with very large velocity. For example, this one, that the M87 active galaxy, the first jet was discovered in 1918, long back, by someone from level 30s. and this is the step-by-step zooming of the center of the M87. So this is the central part which has further been zoomed, and that is further been zoomed to show that something is coming out of the central black hole. So this is the structure of the central black hole obtained by Event Horizon Telescope, but I am not getting into that. That's a completely different issue altogether. So what we get is that the central black holes create jets as well, and the jets has radio structure. So jets are observed also in radio waves. Why radio waves? Because jets are very fast moving matter, and that fast moving matter contains electrons, and there are magnetic fields in the universe. When charged particles accelerate to the magnetic field, then they radiate emission that you have studied during your BSc or MSc electromagnetic classes. So the radio wave comes. So the jets are observed using the radio telescope as well. And the first ever observation of the radio jet. So this is just a schematic diagram. So the first ever observation of the radio jet was by some Indian scientists who used to work in Calcutta later on in radio physics electronics department called Vinay Kumar Dalgupta, MPDG, with Robert Jennison. So this is the old photograph that Dasgupta is working with Jennison in the laboratory, and this is the Manchester's George Drell Bank Observatory. So this is Professor Jennison, and this is Professor Dasgupta. And just for the completeness, I'll show you the first page of the article nature. Okay, so now we know that the combined structure of the active galactic nuclei contains a massive black hole at the center, and jets are coming out of the black hole. So now, since black hole cannot hit anything from the inside of its structure because there is an event horizon, so the outward jet will actually be a part of the infalling matter. So there is a coupling between accretion process and jet structure. So from there, actually, we have a paradigm called jet-disk paradigm or jet-disk coupling. That supermassive black hole or the stellar mass black hole, matter will fall onto it, and part of the matter will come out as a jet. And there are different kinds of black hole jet system. One thing is quasars of the active galactic nuclei. Very long structure, the mass black hole is supermassive black hole, and radio jets are kind of some millions of light years long. So probably the largest possible single structure found in the universe. There is a scaled down version for microquasars, so where the black holes are small in size and the jets are also small in size, but the basic mechanism is the same. The black hole is sitting over there, matter is falling onto it, and some energetic particles are coming out of this thing. And these jets have extremely high velocity, and they are being emitted for long time, like thousands of years or something. So that's why it helps us to understand some very fast, relativistically moving object for persistent time scale. So that is precisely what I wanted to tell you. So this is something like, so the last slide of the talk, that what we can understand by looking at the sky toward the center of the active galactic nuclei. So we try to understand the theories of general theory of relativity and special theory of relativity. We try to understand the general theory of relativity by studying the environment of the central black hole, its curvature of the space-time, redshift, gravitational redshift, etc., and try to understand the theory of special relativity by studying the very fast-moving jets. So that's exactly what I wanted to tell you in this small talk. And this acknowledgement slide, that's some of the pictures I have taken from internet, especially from NASA and from Space Telescope side. And thank you so much for your patience. Thank you.
There are so many religious mythology behind that origin of the universe that is Muslim. So, but the actual thing which we learn in the physics, that what is the reason behind the formation of the universe is the Big Bang theory is considered a realistic thing. So, sir, I want to know that sir, if we look at the expansion of the universe, then we are finding that the universe is expanding day by day, and the universe is expanding day by day. But sir, we are relating that the whole universe we are seeing, which is seems to be such a huge thing was considered that it was compact in a very small particle. So, sir, I want to know that what was the energy that packed such a huge mass into that small particle? Because we know that before the evolution of the universe, there was nothing.
Yes.
But what was the thing that makes such a huge amount of the metals and energy to make it to compress in a small particle? Because if there is not energy at that time, then we cannot do such a process. So, what was the reason behind that?
So, for example, what surrounded that thing kind of thing? Because the entire thing was a single system.
That as you tell that if you see that Newtonian mechanics, then it's said that the planets revolve around the sun due to the gravitational pull. It has been said. But if we see the general theory of relativity which is given by Einstein, it says that there is nothing such as like gravitation which we call. But it is a space curve which was produced by the huge mass of the sun, and due to this curve, the celestial body, anything that comes under that distortion, they start to revolve around the sun. But sir, if we generally look that if we take a tripod and we put a huge mass on it and we pick some glass ball on that, then we see that they initially they rotate about that particular distortion, but at the last stage they get to fall on that distorted mass. But sir, in the case of the universe, that the distortion which is produced by the sun, the our if we suppose our Earth is rotating about that distortion, then why the Earth is not falling on the sun? If we
So there is a gap kind of, rotating these things, and until and unless you snap the string, it will neither fall onto your hand and neither will go out. So it's a balance between the centrifugal force and the gravitational attraction. So here also it was. So only thing is that the gravitational force is modeled into different, other than the Newtonian, unlike the Newtonian. But the gravitational force is there, the centrifugal force is also there. So it's only the mechanical structure through which you experience the process is different from the Newtonian force.
sir, one more question. Sir, as you say that a black hole is that from which no light is evolving, or you say that if anything gets trapped inside a black hole, it is never possible for that to come out from there. But sir, in general, what we have seen on poetry standard, it has been taught of that everything which can emit any radiation, all the radiation, or anything which can absorb all the radiation, is act as a black hole. So such there can be some contradiction that at a particular level we are seeing that object
A region which is always outside the event horizon. Once the matter falls onto the event horizon, so there is no way that some radiation will come out of the event horizon. So all the radiative energies, etc., in connection to the accretion process, they come out from a region which is located far off from the event.
Okay, I think we should